Good morning, everybody. My name is Anton Kuzik. I will be chairing this last morning preliminary session. Our first speaker is Arseniy Kuznetsov. Arseniy is originally from Russia, got his PhD in France, then was in Germany, and now he is a group leader in Data Storage Institute, A-Star in Singapore. He is well known for his pioneering work in dielectric antennas and resonators, so please welcome Arseniy.
Thank you, thank you. Thank you for the introduction, and thank you all of you for coming so early in the morning after the dinner yesterday. So it was not easy, I know it. So, okay, and I also would like to thank Romain who invited me here, so it's really great conference and it's my pleasure to be here. Okay, so today I will tell you about our recent progress in the field of dielectric and semiconductor nanoantennas and metasurfaces. And that's what we have for today. So I will start with a very brief introduction into resonant properties of high refractive index dielectric nanoparticles. And then I will switch to different types of effects which can be observed with these particles. For example, near-field resonant effects such as magnetic near-field enhancement or light guiding in dielectric nanoparticle chains. And then I will go to far-field effects related to directional scattering, Huygens metasurfaces, and also our recent results of very high-angle light bending and high-energy lenses which can be obtained with these nanoantennas. And finally, I will speak a little bit about different material platforms which can be used for these nanoantennas. Okay, so most of you here know about plasmonics, and plasmonics is interesting because it has resonances at optical frequencies, right? So when we have a spherical particle, we can get electric dipole resonance. This is well known. If we want to get magnetic dipole, so spherical shape is not good. We can increase the particle size, but we still will get only high order electrical dipoles. So if we want to get magnetic resonance, we basically need to switch to, for example, split ring resonate or some other shapes. And in this case, when currents are oscillating in the ring, they generate magnetic dipole in the middle of the ring. So like that, you can get both electric and magnetic response. However, it's also known that both of these resonances are all the time accompanied by losses. And the problem is that you have free electrons, so free electrons oscillate, and you have ohmic losses in metals at optical frequencies. And this is a big problem of plasmonics. I mean, you can use it for some applications, but in general, this is a complication. So to avoid this complication, we actually propose and we develop a different approach to resonant nanophotonics. Instead of using metals to generate resonances, we propose to use high refractive index dielectric nanoparticles. And it actually can be shown, for example, using Mie theory. It's quite simple. So that if you have nanoparticle, just a nanosphere, with refractive index higher, with let's say 2 or 3, and you shine light, then you can get a strong resonance behavior at optical frequencies. And for example, here it's illustrated that in a spherical particle like that, you can get both electric resonance and magnetic resonance. And these resonances, they are not associated anymore with free electrons. So they are associated with bound electrons. So basically displacement currents instead of real currents. And that's why if you have transparent dielectric, these resonances can be obtained without basically any loss. And this can be a big advantage. Well, for those of you who never dealt with these particles, I will just show this eye candy picture. So basically that's how it looks like. This is just a silicon wafer, which we ablated by a laser, and then we look under dark field microscope. So you see that you can have all the colors of visible light, right? So there can be blue particles, green, yellow, red, so all the colors can be obtained. And this is associated with silicon nanoparticles, which are generated by laser ablation. Back in 2012, we analyzed these nanoparticles, and we have shown that if you have particle size of approximately 100 nanometer, then you can get a blue color, and this blue color will be just magnetic dipole resonance of these particles, which was quite surprising at this point of time. Then if we increase particle size, we can get these resonances at green wavelengths and at red wavelengths, and you can also see we have magnetic dipole, electric dipole, and also high order mode generated. So I will not go much now into historical overview of this field, but basically if you are interested, we recently published a review at the end of last year, where we basically overview the rapid development of this field over the last few years. Here I would like just highlight the 3 major points why dielectric nanoantennas might be better and might be really complementary to plasmonics. So one of the things is, of course, low losses. That's I already mentioned. The second important thing is nanofabrication-friendly materials. So I already spoke about silicon, which is a very well-developed material, but there are many others which I will talk about today. There are also 3-5 semiconductors, there is titanium dioxide, so materials which are well-known in industry. And also the third advantage, which I will also be speaking a lot about today, is a strong magnetic dipole response. So as I mentioned, even in a single sphere, you get a strong magnetic dipole resonance. And this is in contrast to plasmonics, because in plasmonics, typically, magnetic response is quite weak, and it's actually weaker than electric response. Here, magnetic response can actually be stronger, all the same strength as electric dipole resonance. And this is just a simple comparison. If we calculate scattering by gold, silver, and silicon nanoparticle of different sizes, just in the air, using Mie theory, right? So then we see, if particle size is small, then we can generate just a good resonance in silver nanoparticles. So then this is known, but this resonance is actually in UV spectral range. However, when we increase the particle size to 100 or 150 nanometers, you may see that resonances in silicon become stronger. Actually, they are more intense, and they actually also have higher Q factor than resonances in gold and silver. And this is related to the fact that actually losses of silicon, even in visible spectrum range, are much lower than losses of plasmonic metals. And you may see also that actually there is a big difference here. So you may see that in silver and in gold, for small particles, you only have single dipole resonance. So this is electric dipole resonance. But for silicon particles, you have both magnetic dipole, which is the strongest resonance here, and the second resonance, which is electric dipole. And it's important that these two dipoles, they are actually coherent, and they can interfere with each other. And that's generate a lot of new effects which you typically don't observe in plasmonics, and which I will discuss today. Okay, let me start first with near field. Of course, you know if you have scattering resonances, then you also expect a near field enhancement. And this is something what is well known. And the simplest antenna to check near field enhancement would be dimer antenna, so two particles which are close to each other. So here, if we shine light with polarization parallel to the dimer axis, then similar to plasmonic, we expect here a hotspot, of electric hotspot generated between the nanoparticles. And this is quite trivial. So this is our experiment, the near ensemble measurement, and this is theory, and you may see indeed we can observe a hotspot. But importantly, and this is already different from plasmonics, if you rotate your polarization and put it perpendicular to the dimer axis, you still get the hotspot. So why? Because you also have magnetic dipoles. And in this case, magnetic dipoles are oriented parallel to each other, they interact strongly, and they can generate this hotspot in the middle. That's why for silicon nanoparticles, you can actually generate hotspots for both perpendicular and parallel polarization, just it will be hotspots of electric and magnetic field. And they did here in experiment, you see this hotspot of magnetic field, which was observed using aperture type and so on, which actually can detect both electric and magnetic near fields. Okay, then second thing, now we know that we can generate this near field enhancement, and basically then we can expect some near field coupling. And near field coupling, resonance near field coupling, can be used to guide light at nanoscale, as it was shown in plasmonics. So can we do the same with dielectric? So can we take these resonant particles and guide light? We did this experiment, so this is the chain of silicon particles. So here we use a bit bigger particle to excite the chain. And we fabricated a chain which actually much longer than that one, so it would not fit this room if you look at it. So it has 600 microns of length. And then using ensemble, we detected that indeed there is a mode which is guided inside this particle chain. And importantly, at the end of chain, which is actually 600 microns, we still can see light coming out. So that means with this chain of particles, which has a size of only 150 nanometers, we can guide light of distances over 600 micrometers, which is actually very long distance for nanoscale guiding. Well, these are the loss measurements, so we did measurement for 150 nanometers particle, 220 nanometers particles, and also 340 nanometers particles. And that's what we get. So when particles have size of only 150 nanometers, so it's quite small, we get losses of the order of 34 dBs per millimeter. So it sounds high, but still, so you can transmit light over hundreds of microns, and it's still much better than in plasmonics typically. If we increase further the particle size, and if we go to 340 nanometers particle size, then the losses becomes actually almost negligible. So it's 0.1 dB per millimeter. And this is comparable to what you get as standard silicon photonics with standard silicon waveguides. So basically what it shows that the chain of silicon particles can get as a very efficient guiding system. Of course, you can also use a standard silicon waveguide if you want just to guide light. But importantly, this also means that you can introduce these particles together with silicon waveguides on a silicon chip and use them to integrate different functionalities which don't exist with conventional silicon plasmonics. So integrate them at smaller footprint without introducing losses to the system. Okay, let me now switch to far-field effects. And the first effect, which I think has high importance in our community, is so-called Kerker effect. So what is that? So if you just take a spherical silicon nanoparticle in free space, in air, right, and you shine the play wave, and look what happens with forward and backward scattering. So for plasmonics, again, you expect that forward and backward scattering will be the same, because plasmonic particle, same as every small particle, is actually electric dipole. But since silicon nanoparticle is not just electric dipole, it's electric and magnetic dipole, the scattering in forward and in backward direction, so it's green and blue curve here, they're actually not the same. So if you look at front-back ratio, you may see a maximum here, which means that particle scatters all the light forward, and nothing, almost nothing is scattered backward here. There is another position here. This particle scatters light almost all the light backward, and nothing is scattered forward. There are also positions where a particle scatters light forward or backward, similarly to electric and magnetic dipole. So this basically shows that even a single sphere in free space already works as an efficient antenna, which can not just concentrate light, but also direct light, the scattering of light in different directions. And this effect was demonstrated first at gigahertz frequencies by Spanish and French group here, then by our group in optical frequencies using silicon nanoparticles, and also in the group of Lucas Novotny using gallium arsenide nanodiscs. Okay, so why this effect is so important and why I pay so much attention to explain it? Because actually it gives a lot of opportunities, for example, to do metasurfaces. So how does it work? Imagine now we have a subdiffractive array of such particles, which scatters light, for example, only forward. And we shine plane wave of this array. So what can happen? Since it's a subdiffractive array, so light can only go forward, transmit, or reflect. That's all what light can do. But it cannot reflect because particles do not scatter light backward. So basically what might happen, that light can just go through. So this becomes an array which is fully transmissive, right? So it's transparent. Of course, like just transparent array is nothing special. Glass is transparent. Many things are transparent in this world. But you should remember that actually this array is resonant. So to get this transparency, we excite both electric and magnetic dipole resonance. And due to these resonances, we get this transparency. And when we get resonances, we can control the phase. And then we can use it for designing metasurface to basically manipulate the phase of light in transmission, because we still keep a high transmission through this metasurface. And this idea was initially proposed in a group of Yuri-Kivshai. So this is just illustration how it works. This is basically just an array of such nanoparticles with different sizes, which shifts electric and magnetic dipole resonance. And you may see that here, for example, we have two dips corresponding to these two resonances. Then we start to change the particle size, and this dip disappears. And at some point, we have almost unity transmission through such kind of array. And here again, if we further reduce the particle size, again, dip in transmission appear. So what happens is that in this position, electric and magnetic dipole resonances, they overlap almost ideally and then generate the high transmission mode. So this is basically broadband Kerker condition realization to realize this broadband resonant transmission. And of course, when we have this situation, what we can do, we select this wavelength, and then we start to change particle radius. And by changing particle radius, we can change the phase, which is required by light when it comes through such kind of array. And at the same time, the transmission of this array is kept high. And that's how you design your metasurface. So basically, you just need to change the radius of particles. Phase will be different, but transmission through the array will still be high. And these metasurfaces were demonstrated. For example, this is demonstration from our group. What we did here, this is a gradient metasurface when we gradually changed the size of these particles to acquire the complete phase from 0 to 2 pi. And in this case, when light shines to this array, what happens, it rotates the wavefront of light, right? So light just should bend. So it goes straight, and then it bends at a certain specific angle. And this is shown here. This is a back focal plane images. So you may see for out of resonant condition, we have all the light goes through, so it's 0 angle. But when we are in resonant, then all the light bends. And importantly, you may see that all the other orders of this metasurface, they're all suppressed. So all the light goes only into one direction. And this is, I think, the big difference to plasmonics, because when you have bending in plasmonics, you have a lot of 0 order left. Here, no 0 order. This is important. And the efficiency of such bending is of the order of 50%. Also, these metasurfaces were used not only for light bending, but vortex beam generation, holography, and so on. Oops. Those of you who work with metasurfaces, you of course know that very recently, over the last 2-3 years, there are a lot of demonstration of dielectric metasurfaces which have shown very high efficiency, in particular from a group of Andrei Faraon and also Federico Capassa. So we showed many functionalities, and the efficiency of such devices goes above 80%. However, the approaches which were developed at this work were actually based on very tall structures. So if you look on the thickness of the structures, they are of the order of wavelength in free space. And if you look on aspect ratios, they often reach more than 10:1. So this is quite high. And this is quite difficult if you want to do it on large-scale fabrication. In contrary, if you look on the Huygens approach, which I just presented you, the thickness of the structures is λ/6, so they're significantly thinner and actually much closer to plasmonic metasurfaces. And also the aspect ratio of these structures, not 10:1, but 1:2. So it's actually quite flat disks. So why it's important? When we want to use large-scale fabrication techniques, such as, for example, nanoimprint, fabrication of such structures might be really, really challenging, while flat disks is something that should work very well. And though efficiencies now are a bit less, so we have now efficiency of order 60%, but still the ease of fabrication might play a significant role for that kind of approach. What I showed you before, that was all, of course, done with silicon nanoantennas, and silicon is quite lossy in the visible, so that's why we put all the demonstration around 700 nanometers, where it's still quite transparent. So, but of course, if you want to do the same approach in visible, you can do it. You just need to change material. So in this case, we show that using titanium dioxide, you can also do metasurfaces in the visible spectrum range. And what you may see here is 3 types of metasurfaces generated out of titanium dioxide nanoantennas, and these are gradient metasurfaces. So these are the result of light bending at 3 wavelengths, at 3 different wavelengths. So it's blue, green, and red. So what you see here is spectrally resolved backfocal plane images. So this is the wavelength, and this is the bending angle. So you may see, for all wavelengths, apart from this narrow region, all the light comes through. So nothing happens. It's just light just transmits through this metasurface. But at this wavelength, which is in blue spectral range, it bends, as it's designed for beam bending, our metasurface. So here we can do the same for green wavelength, and here we can do the same for red. So basically, independently, we can create metasurfaces which will work in a very narrow spectrum range for one specific color, or one specific wavelength. So what does it give us? Since it's important, if I take this metasurface, for example, and place together with this metasurface will work for blue, but will not work for green, while this will work for green, but will not work for blue. So that means that I can stack them together, and each of the metasurfaces will work for its own color. And finally, I can work at all RGB colors and basically can work with white light metasurface. The same idea recently was proposed with plasmonic metasurfaces, but however here, the office had to implement 3 different materials, and the efficiency of the device was very low. Here, we expect that efficiency should be much, much higher, and it's with the same material, so now we are working on experimental demonstration of this concept. So yesterday there was a talk of a colleague from my group, Lian Shenan, who actually showed that using the same approach you can also generate, of course, holograms, and these holograms can generate it for the whole visible spectrum range. Importantly, what he also showed that if you actually play with particle dimensions, not just use a disk, but also change the shape of particle, it's possible to achieve much higher transmission of metasurfaces and basically increase the efficiency of metasurfaces. And this happens because electric and magnetic dipole resonance can be overlapped and actually can kind of stick together when you change the particle parameters and change the phase which light acquires. And this is a demonstration how this metasurface, the single metasurface, can work for all 3 wavelengths in the visible spectral range. Okay, let me now switch gears a little bit and forget about Huygens metasurfaces, but speak about a new concept which we developed recently for high-angle light bending. So let us consider an array, diffractive array of nanoantennas. So it diffracts. So when array diffracts, that means if light comes from the bottom, then it will only now allow to go to diffraction orders, right? For example, if we have 3 diffraction orders in transmission, 3 in reflection, then light comes here, and then there are only 6 directions where light can go. So it's all the other directions are prohibited, right? It's important. So it can go to -1, 0, +1, and the same in reflection. So now imagine if every element of our grating is actually a nanoantenna. And nanoantenna can actually have directions where light is scattered and directions where light is not, as I showed you. For example, backscattering can be prohibited, right? In this case, I can suppress all the 5 directions which are allowed, and allow only one direction where light can go. So what will happen in this case? So when light comes, it cannot go in any of the direction which is suppressed by the antenna, but it can go only to that order that I selected. So basically, like that, light comes, and then it will bend into a single diffraction order which I chosen. And why is it important? Why it's so important? Because when we use a diffractive grating, we can just change the period of diffractive grating, and we can change the bending angle as much as we want. So we can change it from 0 degree to 90 degrees, just by simply changing the period of diffractive grating. So, and if it works, then we can realize really high angle light bending. And this is the realization. So you may see we have here silicon antennas. So they are placed in the grating. So we shine light from the bottom. And then on the top, it just bent, almost 90 degrees. In this case, it's 82 degrees bending. And it's very clean. You may see for both polarizations, it comes and it bends at very high angle. And these are the theoretical results. You may see that the red curve is actually the efficiency of light bending into this 82-degree angle with respect to incident energy of light. And you may see here around 50% for one polarization, around 30+% for another polarization. And this is the efficiency, bending efficiency with respect to transmitted light. In both cases, we have around 90% of bending efficiency into this 82 degrees angle. This is theory. Now experiment, so that's how the antennas look like. This is a simple asymmetric dimer, which actually allows us to suppress the required orders. And that's how the experimental data look like. So you may see, indeed, here around 50%, and here around even 40% in experiment, we can obtain for both polarization. And the bending efficiency is more than 80% for both polarizations. OK, so why we would like to bend light at high angles? If we can bend light at high angles, we can also focus light. Right? So we can basically design such kind of lens, and then we can bend from different areas to different angles and so on. So why is it important? When you have an objective, this is a standard microscope objective, which you can buy, 0.9 numerical aperture. It actually can collect or bend light at only 64 degrees. So imagine now if we design a lens which can bend light at 82 degrees. Then the numerical aperture of this objective in free space, what is important, will change from 0.9 to 0.99. So you may see that actually the solid angle of collection of this lens becomes much higher. Of course, you may say that, OK, it's not a big deal, right? From 0.9 to 0.99, probably focus will not change much, the size of the focus. But the collection angle by this lens will change significantly, because the change from 64 to 82 in terms of solid angle is actually very, very high. And that's why we think such kind of lenses might be find many applications. And this experimental realization, so you may see this is the lens, so we basically design it for different Fresnel zones which bend light at different angles. And here you may see for high angles, we have this high angle bending metasurface, which I demonstrated you. And this is the focus of our lens. So you may see we have a nice focus, and if we measure the size of this focus, then we get that numerical aperture of this lens is of the order of 0.94. So this is good. So I mean, I think this is the highest free space numerical aperture demonstrated so far, but it's not 0.99 as we expected. So the question, why? I mean, the answer is very simple. All these measurements are measured using the best available microscope objective on the market, which has numerical aperture of 0.95. And we measure that numerical aperture of our lens is 0.94. So if we look actually on backfocal plane of our objective and compare what actually happens there, so these are the spread of angles for 0.8 objective. This is the spread of angles for 0.9 numerical aperture objective. And this is our lens. So you may see probably it's not super homogeneous, but it's OK, right? It fills the complete circle of 0.95. And if we compare it with the spread of angles of our objective of 0.95, they actually fully repeat each other in terms of size. That actually means that our lens focuses all the angles which this objective can collect. And we expect that it actually focus more of angles, but we just cannot collect them using this objective. So what we do now is to demonstrate that our numerical aperture is indeed 0.99, so we do different type of measurements, which is actually quite not simple, because the lens that we have is much better than anything what we can use to measure it. So we do now this point spread function measurements, basically, to show it. Again, the lens which I showed was working with silicon, and it was working in the red part of visible spectrum, around 700 nanometers. But if you use titanium dioxide, you can again transfer everything to visible part of the spectrum. And for example, here we use this arrays of nanoantennas to show bending at 53 degrees at blue and green spectral range with efficiencies as high as more than 70% with respect to incident light. And also here, using these kind of antennas, we could show a 75 degrees bending with, at the blue and green part of visible spectrum with total efficiency of above 50%. So basically, we can do exactly the same approach and do light bending also in the blue and green part of visible spectrum using titanium dioxide. Okay, I think I have still a little bit of time, and I would like to show some new results which we have with different materials, not with silicon, not with titanium dioxide, but with free-5 materials. And why free-5 semiconductors are so important? So for nanoantennas, they can actually generate new functionalities which you cannot get with silicon. And this related to, for example, nonlinearities, because free-5 materials, they can have a second-order nonlinearity, but also they can generate some active functionalities because they can emit light. This is something what silicon cannot easily obtain. And recently there was some interest to that, but mainly all the works were done with gallium arsenide-based materials and also gallium phosphide. So what we propose to do is to work with gallium nitride. So if we actually look at materials, so which we compare silicon, titanium dioxide, gallium arsenide, gallium phosphide, and gallium nitride, you may see them here, that you may see that gallium nitride provides the best absorption, I mean the lowest absorption coefficient through the whole visible spectrum, and also going even down to 300 nanometers. So basically you can use the material through the whole visible spectrum and use it even in UV spectral range. At the same time, the refractive index of gallium nitride, which is red curve, is still above 2.5, which is good enough for us to do nanoantennas. But there is a small problem with gallium nitride, and I think Patrice Genvet yesterday demonstrated that they do gallium nitride on a membrane, which is quite complicated fabrication process and difficult to handle. So the reason is that if you grow gallium nitride in a standard process, right, like you do it in LEDs, you typically use sapphire substrate, and then you grow epitaxially a very thick layer of gallium nitride. And you need it to be thick to actually become a good crystalline phase of gallium nitride, because you grow it directly on sapphire, then crystal is not of high quality. So basically that means that if we want to do a metasurface now, we need to design a metasurface which will be gallium nitride metasurface on a gallium nitride layer. And that generates some challenges because the substrate has a very high refractive index. Still, if we use smart approaches, for example, waveguiding approach, where we use tall pillars to generate different waveguide modes with different refractive index, then we can obtain the 2-pi phase change with high transmission, even in this situation. And this is demonstration of shot metasurface, which is done for light bending using gallium nitride. And this is the experimental result. So red curve is the bending for here S polarization, here P polarization, and black curve is theoretical calculation for this metasurface. So you see they match well, and the results that we obtain for bending is more than 60% efficiency with respect to visible light. And I would like to highlight that here we demonstrate this efficiency at blue light wavelength. So it's 400 plus nanometers. So we show how gallium nitride can be used in the whole visible spectrum. Of course, it can be used not just for bending, but there can be more sophisticated functionalities. And here we design a similar metasurface, but which bend one polarization in one direction and another polarization in the other direction. So you may see here, this is P-polarized light. It has a 60% efficiency to bend towards -1 diffraction order, and S-polarized light is bended towards +1 diffraction order. So it can be used as a beam splitter. Okay, and with this I come to conclusions of my talk, so I hope I could convince you that actually dielectric nanoantennas, they actually provide a lot of different opportunities and functionalities which plasmonic doesn't have, and they basically can become a complementary to plasmonics for many applications, or substitute plasmonics for many applications. And what I highlighted mainly, there was a near-field effects related to magnetic near-field enhancement and also light guiding at nanoscales with very low losses, and also some far-field effects, such as Huygens metasurfaces, such as high-angle light bending, and also high numerical aperture lenses, which can be generated using these nanoantennas. With this, I would like to acknowledge my group in Singapore, and in particular, I would like to say that we're still hiring, so we have one position for a theory person in our group, so if somebody is interested, please approach me. That's all. Thank you for your attention.
Thank you very much. Questions, please. Wait for the mic.
Okay, nice talk, Arseniy. Maybe you can explain a little bit, let's say I have a little bit of problem to understand really how you get this 2 pi phase change compared to the other dielectric meter surface where you said they use the SIG, like wavelength SIG, but you're using only lambda over 6. And you change only the diameter, let's say, of this cylinder.
Exactly.
So where is this phase change coming from? Because it cannot be, or is it like a propagation effect like in the SiC?
Of course not, of course not. So this is a resonant phase change. Remember capacitor metal surface with V-shaped antennas. Why V-shape? Because there should be 2 dipoles, one in one arm, one in the other arm. Why 2 dipoles? Because each dipole resonance will bring you a phase shift from 0 to pi. But when you have 2 dipole resonances, you can get this phase change from 0 to 2 pi. That's why you get V-shape in a capacitor antenna. But here in dielectrics, I don't need V-shape, because even in a single disk, I have 2 dipoles. It's electric dipole and magnetic dipole. So each of them provide me pi, so together they provide me 2 pi. I don't need to use the Z component. Just to have 2 dipoles is enough to get the complete 2 pi.
And so you change the position of these 2 with the diameter?
Yes.
Okay, I see.
That's how it works, yeah. Please go ahead.
It's very interesting with this flat lens with high numerical aperture. You mentioned in the talk that your lenses, commercial ones, cannot even measure the image. Why not make a collection lens out of your flat optics, and then it's as good as the one that is focusing on light, and hopefully that can measure the image you've generated?
This is so far is the best flat optical component, so you need to fabricate something which is better to measure it, right? So that's the problem. That's why you need to use some other detection methods. What we do now is just try to use points, like very small point source, and try to collect it through the lens and measure the point spread function. So basically to try to measure what is the real NA. Because if we just focus light with our lens and then try to collect on our side, there are no optics which allows you to get these spread of angles. You also cannot use the H method because the spread of angles is so high you cannot put there anything. So it's very, very large angle.
Have you?
And then how you measure it?
By comparing to well-known numerical aperture which is smaller. By calibrating.
Which is well known. They should be well known which is higher than your lens.
With lower, but then you can see how much more light you collect.
Oh, the collection of light. But then there is another point that actually the efficiency of lens, of course, not 100%. So, and then you cannot really calculate that if you don't know it exactly.
All right.
More questions, please.
Yeah.
So in the light guiding in silicon nanoparticle chain, what is the substrate of your?
So it just surrounded. It's actually, I mean, in the first case, when we considered 150 nanometers silicon, it was quartz substrate. So it was amorphous silicon deposited on top of quartz substrate. But in the last case, when we demonstrated 0.1 dB per millimeter, that was a SOI wafer covered by silicon dioxide. So it was fully embedded to get that kind of low level of losses here.
So in SOI, it become a freestanding, the nanoparticle? Or
yeah,
how?
I mean, it's surrounded by silicon dioxide.
Okay.
Yeah, maybe the last one.
Thanks for the talk. The usual approach to get more numerical aperture is to use oil. Do you think that's something you can do with your new lenses to really beat the 1.45, which is?
Yeah, of course. But when you're using foil is a bit of cheating in a sense, right? Because you don't change your collection angle. You just change the refractive index of environment. So the maximum collection angle, even in oil, is still like 64 degrees or something. That's what brings you the numerical aperture of 0.1, 0.4, 0.45, what you can buy now. So of course, we can use this approach to get the same high bending angle, but in oil, and then we expect to get numerical aperture of close to 1.5 plus. But this requires redesigning, so we didn't do it yet.
But it's the next step.
Well, yeah, I think so, yeah. Thank you.